Partitioning and layering is a technique to build software applications in a way that makes them easier to change. This screencast outlines the basic principles of partitioning and layering, and the subsequent screencasts and codecasts talk about how to take these principles and apply them to a specific application that we will change over the course of the screencasts and codecasts. With the knowledge thereby gained, you'll be able to apply these principles to your own applications. We cannot wish away the fact that software applications change. Requirements change as the users understand more about the application requirements, and they change as the application evolves to meet new challenges from the marketplace. Technologies change, and the application has to be able to adapt to those changes. And of course, bugs have to be fixed. The major way to accomplish these tasks economically is to minimize the changes to the application that have to be made when we modify a software application. In other words, software must evolve and adapt in as simple a way as possible. Using layers in a software application isolates the parts of an application from each other in order to minimize the impact of a change to one part of an application on another. It also allows focused unit tests to be written, so those tests a small subset of functionality so we can be sure the pieces of the layers and then the layers themselves work properly. Partitioning and layering is one of the techniques of code refactoring. In order to understand how to partition and layer an application, we use the techniques of object-oriented programming. While object-oriented programming has been around for a while, we have learned a great deal in the past 20 years of how best to apply the techniques of object-oriented programming. The four important concepts for partitioning and layering are the difference between a type and an object, the definition of what a complex type is, to understand what composition is, and to understand what an interface is all about. The first concept to be understood is the difference between a type and an object. A type is a definition containing data and methods. An object refers to the memory allocated to a particular instance of that type. For example, looking at the employee class here, we see it's composed of data, for example, the string name, and behavior, which in this case is one method called pay. The string name is an example of a simple type. The class employee is an example of a complex type. An object, then, is usually an instance of a complex type. For example, the particular employee type instance that was created here. So here we have a new employee object. Here we have used composition to build the auto class. The auto class is composed of two other classes, the engine class and the wheel class. Since it's composed of other objects or built from other objects, we call this an example of object composition. We say then that the auto class depends on the engine and the wheel class. Of course, object composition introduces dependencies because now how the engine class is constructed and how the wheel class is constructed influence how the auto class behave. So the whole idea is to write your applications so the dependencies of one type on another are eliminated or minimized. So what we want to do here is to make the types dependent on the type's behavior, not its implementation. The behavior being the particular methods of the type, not the particular data that's used or the way the data is manipulated inside the method. When we accomplish that, then we can build unit tests that verify that a type's behavior is correct. And the way we accomplish this is using interfaces. Let us define these two interfaces, iEngine and iWheel. Interfaces have only methods. Properties are just a shorthand for a type of method. Hence, they only describe the behavior associated with the interface. Wheel, turn, engine, stop, start. So now let us rewrite the engine and wheel to implement these interfaces. Once these classes implement these interfaces, we can now use these interfaces to build the auto class. So now the auto class, instead of using object composition, is using interface composition. The auto class is now independent of any particular engine or wheel class. If we change the engine class to fix a bug or enhance it or use a diesel or a Wankel engine that implements iEngine, the auto class does not have to be rebuilt. In addition, we can write focused unit tests for the engine and wheel classes to make sure they implement the proper behavior. So using interfaces allow objects also to be dynamically composed at runtime. So long as the engine or wheel class implements the appropriate interface, we have minimized the dependency. We have not eliminated the dependency because the auto class is still dependent on the behavior or the behavior of the engine or wheel class. And this is a very important point. This dependency on the behavior is considered to be essential coupling. It's based on the part of the real-world application that you're modeling. You can't eliminate it because without it, you would not have an application. What we want to do in partitioning is to remove the inessential coupling. This kind of coupling is an artifact of how you build your application. It is dealing with the programming details of how objects are implemented, and we want to minimize this type of dependency. To give you an analogy, think of an electric socket. We have a wall socket. This wall socket is an interface. It removes the inessential coupling due to the physical shape of plugs and appliances. So long as the plug matches the way the wall socket is physically constructed, it doesn't matter how big the plug is, how long the wire, or what the appliance looks like. On the other hand, this interface cannot remove the essential behavioral coupling of voltage and amperage of the standard current, because that is what the appliance actually depends on. In the process of doing this, we actually have made our application more complicated by introducing interfaces. Every time you insert a level of direction to a program, you, of course, increase the complexity. And this is one of the enduring dilemmas of application partitioning that we will see over and over again. The tension between simplicity and the ability to change your application easily. So before you start putting interfaces on everything, you have to think where they're appropriate. And as we'll illustrate in each unit of this track, you have to think of where the fault lines in your program are and put interfaces there. Of course, these fault lines will change as your application evolves, and you can refactor appropriately. Nonetheless, it's almost impossible to refactor yourself out of a bad design. The previous auto example demonstrated the advantage of using interface composition over object composition. You might ask, what about inheritance? After all, it's been drummed into us that inheritance is one of the most valuable pieces of object-oriented programming. So let us ask ourselves, is it good to have an inheritance chain such as the one we have, where a class called racing car inherits from high performance car, which inherits from auto? What inheritance essentially does is define the implementation of one type in terms of another. Class inheritance is defined statically at runtime. So one obvious disadvantage is you cannot change it dynamically at runtime. However, there is a much more serious disadvantage. You will have to understand the behavior of the base classes in order to override their behavior, because you've put in an implementation dependency. And this is exactly the type of dependencies we're trying to avoid. Let's make this a little clearer. Let's look at our racing car example. Suppose we have a class called high performance car and racing car inherits from it. Suppose we wanted to override the start method in the racing car class. Do we need to call the start method in the high performance car class, in our derived class, or are we going to completely replace it? To answer these questions and other similar questions, we need to know the details of the implementation of the start method in the base class. Hence, the famous phrase, inheritance breaks encapsulation. Because without knowing the details of what the base class does, you cannot decide how to override a method. It would be much better to use object composition instead of class inheritance to avoid these problems. In fact, the best thing to do would be to use interface composition. This will enable us to restrict inessential coupling and make interfaces easier to modify. Restricting yourself to essential coupling is not enough, though, nor is using interface inheritance or object composition enough. You want to make your interfaces easy to modify. Even within the implementations themselves, you want to minimize dependencies so that the implementation has to be easy to modify. Because at some point, you actually have to have an implementation. Design patterns increase the flexibility of your application. Essentially, what a design pattern is a solution to a programming problem that has occurred so many times before that it essentially deserves a name. And in the subsequent units, we shall be referring to several different design patterns. So to make this clearer, let's take a look at a design pattern we might use in our electrical analogy. Even with a wall socket interface, how do you design an appliance to work with 110 volt or 220 volt electrical grids? We use, of course, an electrical transformer. So the way to think of an electrical transformer is a pattern to modify the behavior to minimize the effect of the essential coupling of voltage and current. So to summarize, to partition and layer a software application, you want to reduce the coupling or dependencies of complex types on each other. And the lab associated with this unit will demonstrate how to use interface inheritance to minimize the dependency of an application. Partitioning and layering is achieved through a mixture of design and programming techniques. This will help you to minimize the impact of change on your applications, as well as build focused unit tests. Develop your classes using interfaces rather than concrete classes wherever possible. Prefer composing your classes with other classes rather than using class inheritance. And use patterns to further minimize the dependencies. Throughout the rest of the subsequent units, we'll describe how to do this in more detail.